My name's Andrew Richards. I'm the CEO of CodePlay, and we produce compilers and tools for heterogeneous systems, so things like GPUs, DSPs, stuff like that. And we're based in Edinburgh, in Scotland. So what I'm going to talk about is, well, it's not just about programming languages, but it's also how do you build programming models for heterogeneous systems. And I'm particularly going to talk about what I'm involved with a lot, which is standardization. I'm spending an awful lot of my time dealing with the politics of standardizing across lots of systems so that you're not just stuck on one particular processing core. So that's a lot of what I'm going to be talking about. I'm going to be talking about some of the things that are happening in the standards and how that is going to make it easier for people to design their own programming models. So I suppose this is the sales pitch about CodePlay. We've been producing compilers for particularly graphics processors for quite a long time, since 2002, when we're even doing stuff before then. We are very heavily engineering company, so we build these things. And I should say that predominantly we as a company deal with consumer electronics, smartphones, things like that. So if you're researchers, you may deal with GPUs and things like high-performance computing. We're much more dealing with GPUs and things like graphics. Actually, so I can understand better the audience, could I get people to put up their hands? First off, whether you're in academia, so whether you're students or researchers or something like that. Right, okay, almost everyone. And who's in industry? Okay. And how many of those of you who are in industry are actually in research rather than kind of actual production development? Oh, just one, right, okay. So quite a lot of people are actually using these systems for real. So that's good. So it's gonna be a bit of a crossover. So this is about how do you make these systems easy to program for real world software development, but a lot of this is about the ideas for research and what we need to solve. I'm going to show some slides that I did last minute, hurriedly yesterday, and actually almost everyone this morning has showed almost exactly the same slide. So maybe we'll skip through them, but well, people show slightly different versions of it. So this is about power consumption over time for the stuff that I came about a lot, which is video game systems. I've got various video game systems. It's kind of similar for PCs. But you'll see when I started back on the ZX81, it was typical for a processor to be about 1 or 2 watts. There wasn't even a heatsink, let alone a fan on those things. And what you'll see is, over the years, power consumption went up, as well as performance going up. And what isn't on here is, actually, have I got a pointer? Yeah, I've got a pointer. See, the line goes up like that. And it suddenly starts going down. And the bit that's missing from the graph is that actually people designed processors that went up here. And sometimes hardware designers will talk to you about the very painful time they had designing these processors and taking them to PC manufacturers and saying, we've designed this new processor, it uses up 1 kilowatt. And the manufacturer is saying, we're not going to buy this. So what you see is a sudden change of direction. And actually for game systems, I can't remember if the next slide is not PCs, but for PCs it's going to be similar. You're going to see the predominant market for clients, maybe for the PCs and video game systems that you buy, power consumption is trending down. There's a little bit of a curve up here because on video game systems you have a big generational change from PlayStation 3 to PlayStation 4, but you'll see it's still going down. And that, I would expect, will be the continuing way that people are doing things. People are moving towards more lower-powered devices. It's a total change in direction. This is the other side of it, which is the clock frequency over time of main systems. And what you'll find is that they just went up and up and up and up and hit a peak at about 3 gigahertz. And very few systems go beyond 3 gigahertz. And in fact, in some cases, it goes down. And this blue line is the one that you saw from Qualcomm, which is showing the speed at which mobile systems are catching up to mainstream systems. What this graph doesn't show, again, is what happens if you actually leave your mobile phone on running at this speed. It was described quite literally in one talk as it would literally burn a hole in your pocket. So the reason that phones throttle themselves down, so they run at this, they temperature sense it, and then they throttle it down, so that what these devices can do is they can respond very quickly to a press, but they can't continually run at that kind of performance. It's heat. Heat more than anything would kill a mobile phone. So we're in a new area of heterogeneous computing, which again people have talked about. The one that I do, because it's shown now, because it's studied quite a lot, is Apple's processor designs. And what you'll see is these are their generations of chip, and people actually tear these apart and have a look at the kind of space that's used on the chip for the different components. There's kind of an interesting story. So the story I used to tell is about the GPUs getting larger and larger compared with the CPU. And actually, in the most recent generations, that's not entirely true. The GPU is quite large, and it's larger than the CPU. I mean, what you can't tell is the CPU is massive. Their CPU is extremely wide. But there's a huge growth in other stuff. So their latest, this is in the iPhone 6, the CPU is actually a very small part of the chip, and even the GPU is too. There's a huge amount of extra processing power that's being put on this system. And this is showing that we're not just going from GPU computing, we're going into a whole heterogeneous computing environment where there's an awful lot of stuff on here. I mean, some of it's cache, but there is an awful lot of other processors that are being put on these systems for special purposes. And this is a slide that I've been showing for years. Look, it's from Supercomputing 2010, but it's still true. It's for an old generation of hardware, but it's something I've nicked from Bill Daly, who's the chief scientist at NVIDIA. But the numbers are kind of they're still very relevant. What he's done is he's showing you the power consumption of different units on a chip. And see this tiny thing here? This is a double precision floating point unit. And what he's saying is to do an operation takes about 20 picojoules. Now, when I started on the ZX81, you'd have to write that in software, and a huge amount of software to get that to run. And now, it's just a tiny dot on a chip. Look at this. This is reading from local registers to this unit, 26 picojoules. So it uses up more energy taking data from a local register and putting it into a double precision unit than it actually does to do the processing operation. But then look at some of these other numbers. 50 picojoules, so 2.5 times as much to take it from a kind of small memory. From a further memory, it's nearly 10 times as much. But once you start looking at figures like going across to the end of the chip or going off chip, once you're going off chip, the amount of energy use is 1,000 times the cost of doing what's probably the most energy-intensive operation you could expect to do as processing within a processor. Now, no one's programming language is designed to reflect 1,000 times difference between the energy consumption of reading data versus processing data. In fact, in most programming languages, accessing data is considered free. And that was certainly true when a lot of today's programming languages were designed. It's effectively free to access the data. The issue was doing the processing. Now it's the data movement and the distance on the chip that has a dramatic effect on the actual power consumption. Now you may think, I don't measure power consumption, but these chips are designed to achieve efficient power consumption. So in terms of the system that you're dealing with, they're designed to hit a power budget. And so yes, this is having a dramatic effect on the performance of your software. So one of the other big issues, which I suppose is easier to understand from a programmer's point of view, it's more like what we're used to, it's got these pipelines, and then it's got kind of short-circuiting within these pipelines to join the stages together. And what that allows is these CPUs to respond very quickly to decisions. So you can have very branchy code and go off on a different route very quickly. You can respond very quickly to user input. Whereas this kind of processor, which is what you would get in a GPU, is throughput processor. So a huge amount of execution units, but that can process a very large amount of data with a very high amount of throughput, but very poor response to quick decisions. So these two extremes deliver different power efficiency for very different kinds of software. So really what this talk is about is, if we're software developers, we get given this hardware and there's nothing we can do about it. We just have to find a way of programming it, and it's changing on us, and we're having more and more special purpose cores appearing. We had the talk about FPGAs, which are extremely weird for programmers to deal with. How do we handle this in software? Now, when CodePlay started as a company, really it was a completely different programming model for each different core. So you're given a core, and I describe this very much as a vertical programming model. So you'd get a core and you'd get an entire programming model. You get the compiler, you get the debuggers, you'd get the language, you get the runtime, you get the operating system support, and it would all be very different. And maybe at this level there's a standard like OpenCL or OpenMP or something like that, and maybe there isn't, maybe they're all completely different. But what we're trying to do in the industry is move in this direction where it's more of a horizontal approach, where each different core has different drivers, but there's a kind of standard binary format which would allow you to add your own languages, your own debugging tools, your own whatever on top, and then you can have your own libraries and the user software. Now, for us as a tools vendor, this lets us stick stuff in here rather than have to build an entire stack for a new bit of hardware. But it's also opening to the point where even if you're a software developer and you have your own domain of expertise and you want to have a programming solution which is right for your domain, you can do it, and different cores can be plugged in underneath. And given the release schedule, probably when you start writing your system, these are cores that you can buy may change. New devices are coming along. So this approach is much, much better, and it's going to open up much more opportunity for you to take your own languages and run it on these kinds of systems. It's just repeating it basically, but we're also seeing, we're seeing both the binary level with OpenCL SPIA and HSA, but we're also standardizing the languages higher up. And one of these, SYCL, is a group that I chaired, which is a C++ for OpenCL, but there are plenty of other things coming along that are at different levels. And we're trying to start to look at how we standardize debugging, which is a really difficult problem. So OpenCL SPIA is actually available now. So this is a binary format for OpenCL, based on the Clang LLVM compiler toolchain, which is open source. And so today, you can write your own languages, compile it down to this LLVM intermediate representation. You don't have to use the LLVM compiler toolchain. You can write your own compiler toolchain, compile down to that. And this is going to allow you to write a language that runs on multiple cores. It's not supported everywhere, but I am expecting it to be supported by an increasing number of vendors. So this is going to become much more viable as a way of being able to bring your own languages and run it across lots of different processing cores. HSA is another one that I'm also very involved in. It's at a lower level than OpenCL and SPIA. The provisional specs are out now. It's a little bit hard to actually work out what it's getting at HSA, but it's much closer to the hardware level, and it allows you to write much more complicated languages, and it has a much easier to use memory sharing model, which allows you to massively reduce the cost of offloading work to a core. So on an HSA system, if you want to just offload a loop, you can do it at very low cost. Whereas with OpenCL, if you want to offload a loop, there's quite a lot of software and runtime and operating system stuff that has to go on in order to enable you to do that. So I'm going to talk about what do you actually need in a programming model for a heterogeneous system. The things that we want to abstract away to enable people to move software between all of these different cores are the differences between throughput versus low latency processor cores. You want to make that easy to deal with. Different forms of memory and data sharing. No one really agrees. I mean, OpenCL and HSA have a slightly different model of different set of capabilities in terms of how data is shared between the CPU and all of the devices in the system. We need to abstract away different compilers and different instruction sets between all the different things. And we also want to abstract away performance and optimization differences. So you can write the code once and it's going to run reasonably fast everywhere. So I'm going to talk first about how we deal with the differences between throughput versus low latency cores, because it's probably the easiest thing to start with. So a low latency CPU on the right, it can respond very rapidly to inputs and conditions, and code is going to be either single-threaded or complicated threading code, for which people may be quite familiar. Whereas on a throughput core, things are going to be broken up into kernels or tasks, and then basically you're going to offload a loop onto one of these data parallel cores. So what you want to do on a throughput core is build tasks into task graphs, so graphs of things that are going to be executed, and you say, right, this is going to execute, and it's going to create outputs that are going to this thing, and it's going to create outputs going to this thing, and this task can be run independently. There are other approaches. There's things like futures and various stuff. The most successful, particularly from the high-end game developers who do this stuff, is to build task graphs. You get much better performance right from the start. It's much easier for people to understand. Yes, you have to build your software to be parallel, but it's going to be fast. So I generally recommend that that's where people start as an approach. On throughput cores, you really want data structures to be arrays where possible. OpenCL, it's kind of, you've got virtually no choice. But with CPUs, obviously you can handle complex data structures, but arrays are a lot better for throughput cores. The other thing is that data movement needs to be part of your task graph. Don't just think about the actual execution, you have to think about the data movement and how that fits into your task graph, because that's got to be parallel. So the approach that we took in SYCL, which is our C++ for OpenCL, is that data parallel loops are written as a C++ parallel for, which is a function, it's templated, it's really standard C++, everyone does it the same way. So I'm saying we did it in SYCL, it's pretty much anyone who's going to do this with C++ is going to do it this way. We add an extra and interesting thing, which is that we have two levels of parallel for, because GPUs have several levels of parallelism. They have, in OpenCL, it's work item and work groups. In NVIDIA, it's kind of warps. There's all sorts of different names for these things on different systems, but basically we deal with that as a parallel for inside an outer parallel for, and it abstracts it away quite nicely. Lets you do nice things with templates. And the other thing that we do is we actually separate data storage, which we put in buffers, from data access, which we put in what we call accessors. We've used this model quite a bit on various systems. SYCL, we've taken it to a whole new level, really, and you request certain kind of access to data, and that allows the system to work out for you what the best approach is for accessing data. And moving data between different systems. And I recommend this approach. You'll have to look at the spec to see how we do it. But it doesn't require any special language features. It's something that's built into C++. If you're doing it in other languages, I do recommend that you have a look at this approach, because it's at the library level, it's extendable into the future, and it really lets you highlight a lot all of the dependencies between your task graph and get maximum parallelism and the most efficient data movement. The other thing that we do is we build up the task graph. We don't execute immediately. We say to the user, you're telling me stuff that I'm going to do in the future. I'm not necessarily going to do it immediately. Again, that allows the maximum level of parallelism. So different forms of memory and data sharing. So this is kind of what I was talking about before. A equals B plus C. There are actually 3 different data movement operations, but in no way are they highlighted in the language. It's the plus that's highlighted. And as I showed, accessing A, B, or C could be 1,000 times more expensive than the plus, or it may be just 1 times more expensive than the plus. So this kind of is a different data movement, but there's no guarantee that this is any faster or slower than the other one. So it's not really explicit in programming languages. So what we want to do, because it has such a huge amount of impact, we do want to make it easy on the programmer, but we also want to give programmers control over something that's a massive high cost. So we want to make it not too hard for people to hide the implementation details of access to the data, at the same time as giving them control, because easy control, because that's how they're going to get extra performance. So this is kind of the example I've got. If this is, this is the distance from the core, and this is kind of pretty typical for today's devices. Huge kind of long range of stuff from registers which are attached to an individual execution core, registers which are shared between execution cores, on-chip memory, on-chip memory going into that's shared between a whole group of groups of execution cores, and then you might have DRAM attached to a particular device, then you might have DRAM shared across the whole system. So there's a massive long difference in distance from the processing core. And at each level, you may well have different rules about what sharing is allowed, how you address them, pointer values to all of these memories may be different, pointer types between all of these different may or may not be different. The coherency may vary between all of these processor cores. So there's really quite a lot here that we want to abstract away, especially as this graph is going to be different for different devices. So what happens when we write A equals BI? The contents of BI are going to be moved into a register, but they may have to be moved through multiple of those levels. So here's BI out in DRAM here being moved into registers. And there's 2 main classes of approach of managing this in memory, right? One is a caching system, which you would get in a CPU, is it's going to automatically move BI up the hierarchy. And there might even be an extra level of hierarchy on a CPU. There might be a hard drive out here for virtual memory, right? So the system is going to move it around up to your execution core. And your execution core may have to stop and wait, or maybe it goes off and does something else, or maybe it doesn't. So this is data moved in on demand. This is, I'll come back to it. The alternative is DMA, in which case you have to move all of the contents of B up into local memory. So OpenCL and GPUs, they move between these 2 different things, these different approaches. But these are the 2 extremes. One is you preload the entire array into your chip, and the other is on demand, you load the data in. So the differences are in DMA, it's very high latency because you've got to pre-move all of your data, whereas caching is very low latency, so you can access data quicker. But caching in a virtual memory environment requires a lot of support in the operating system. So it's very difficult for you to just say, I'm going to buy this chip from somewhere, I'm going to stick it in my system from an operating system that I've got from somewhere else, and a CPU that I've got from someone else, and have a kind of virtual memory caching system that goes through the whole thing. Unless your operating system supports it, and most of them don't, it's actually very hard to do a caching system for heterogeneous cores. Much easier to implement a DMA system. And so that's a much more future-proof kind of approach, even though it may be harder to use. And then there's the issue of bandwidth. Probably caching is lower bandwidth, and probably DMA is higher bandwidth. What's the difference? Nobody knows. And it's going to be different on different hardware, and I have huge amounts of arguments with people, and we don't know until you build it. And that takes 3 years and several $billion. So it's a very expensive question to answer. Yes?
But if you have lower boundaries, will it be lower power consumption then? If you
what's the power? Yes, what's the power consumption difference between these two approaches? Spend $1 billion, design a system on chip, then write the software, and then find out. I'll tell you in 4 years' time. We've been in this situation where people have designed these things and not known the answer. Which is lower power consumption, which is higher power consumption? Yeah. We have these arguments. I try and work it out. I would argue that DMA is probably, as a safer bet, DMA is going to be lower power consumption. Not everyone agrees. I think most people would agree that the caching approach is higher power consumption, but what's the difference? Is it 1%, 5%? If it's 5%, it's worth it. If it's 100%, then it's harder to argue. But I don't know the answer. Oh, really? Gosh. I haven't got very long. So this is, I'm going to highlight one of the main differences actually between the programming models. Separate source versus single source. So separate source is what you get in OpenCL, whereas single source is what you get in things like CUDA or OpenMP or C++ AMP. Separate source is where you write your kernel as one source file and you compile it down to a binary for that hardware. And so the CPU code is in one source file, it goes through one compiler, and the device source is in another source file, and it goes through another compiler, and this I'll come back to. So the advantage of separate source, you can do stuff like, it's good for low-level hardware hackers because they can modify the code on the fly, actually while it's running. That's kind of fun. It's much easier to implement, but from a programmer's point of view, data types actually need to be hand duplicated and checked between the different devices. You need to check that the data types are going to have the same layout and that they're the same and that you've matched things across. You can't do C++ style templates across device boundaries. You can't instantiate code across host and device boundaries. Whereas single source is compiled offline, so you can't modify it on the fly. But you can share source and data types between the host and device. You can write a single device template that'll instantiate code for both CPU and GPU or whatever it is. And so it's a much easier, more natural programming model for ordinary people. So when we come to compile it, separate source, yeah, we have several compilers, so it's pretty obvious what we do. If we have a single source compiler that outputs CPU code and device code, what you find is then you're forcing people to use a single compiler, which may not be optimal for any of these devices. It's a real problem for people. It's also a problem for those people like us who design these compilers. You have to integrate it all together and release it all at the same time and test it all the same time. It's really tough. So in SYCL, we use a special approach, which I really like, and it works very well, which I call shared source, which is that the same source file gets compiled by multiple compilers, and the device compilers extract the kernel for each device. Now you need to output some glue code when you compile this in order to get the host compiler to know how to actually run these things. But this approach allows you to have completely separate compilers so that we can choose GCC here or Intel C++. You can choose the compiler that's optimal for your CPU, and then you can choose the compiler that's optimal for your device. And you can even do things like if-def for the different processor architectures. So it's quite a nice model. It looks like Magcheck. It's a little bit strange when you look at it because you've got a single source file and you think, how is it being compiled? But actually, once you look into it, it's not Magcheck. I've got less time than I thought I had because we've got a bit of time. But I will jump to the end and maybe you can ask me some questions. Okay, we'll spend a bit more time then, and then if I won't be offended if you think, oh, there's another talk on at the same time. Yeah, it's okay. So when you look at SYCL as a spec, you are going to assume that this is the approach that it's taking, and actually it is taking this approach. we don't put in the spec how this works, but because it's implementation defined, but it does mean that you can do things like you as a developer can write parallel sort. You can put my type and you can define your type and make it all work. So it's quite a nice approach, even if it looks very strange at first. So another thing that we have to do is balance abstraction. And this is one of the problems that we've had when we've actually taken high-level programming models to developers. You say to developers, yeah, this is going to make it a lot easier for you to optimize really complicated code on a particular device. But the reality is, if you give people a high-level abstraction, somebody in that company or in that development group is going to go, yes, but I know there's a special hardware feature, there's a special thing that's going to work in my algorithm that I want to use. So you've always got to think about, if you're going to deliver a programming model to people, to real developers who are going to be doing real optimization work, you've got to answer the question, how do you drill down to get to the low-level performance details of a particular system? So even if you're giving somebody a high-level thing, which is a good thing, we've worked with a lot of developers who say, I'm going to write everything in assembly language. Somebody comes along with a new chip, all of their software needs to be wiped out. It's a stupid thing to do it totally low level. But if you only do it at a high level and don't allow people to drill down through, they will get stuck in the optimization process. They will hit a blockage and they'll go, I won't use this system because I'm blocked from what I need to do. But if you give people low-level access, how do you maintain portability? So you've always got to think about, there's no point, as some of our customers have done, is just really optimize some software for a particular chip. Because by the time you've got it really optimal, there's going to be a new chip out. So you've got to enable software to be able to move to new systems whilst at the same time being able to drill down to low-level performance details. It's a balance that you've got to think about to get right, and it's tough, but it is something. If you've got low-level access, you want to do automatic optimization of software, right? Which is a good thing. Developers do want to be able to write something and go, compiler, optimize this for me. But the problem with getting the compiler to do all of the optimization for you is what happens if someone comes along, they've got good performance and there's a bug fix, there's a little bit tweak that they have to do to fix something, a little bit of change in the software that they have to do, and suddenly their software runs 10 times slower. It's a massive problem for them, and they can't explain why it's happened. And we've had a lot of problems as a company because you put in this optimization, you think, gosh, this is really clever, it optimizes this example here. They make a small change and the compiler goes, oh, it's not safe for me to optimize that. I won't. How does the compiler explain to the user, well, that code was written in a form that I can optimize and that code wasn't? And suddenly the user has to understand alias analysis coming out of a compiler, and that's really, really tough. And so it is a real problem how you produce a system for people that gives them consistent enough performance so that they can expect to be able to modify the source code and it not suddenly go much slower, whilst at the same time being able to optimize the program for them. And the other thing is, it's the same point, which is providing information back to a user that they can act on. So if a developer is going to be optimizing something, you need to be able to communicate to them why there's a performance problem, whether it's to a profiler that's analyzing their source code or something. You need to be able to communicate what they might be able to do, where their problems are and where their problems aren't. I spend an awful lot of time recruiting students out of university, graduates, and they think they know a lot about optimization, and they start optimizing something and they go, I've optimized it loads and it hasn't gone any faster. And the first question I always ask, drill into people's heads, is do not do any optimization without profiling your code first, because you have no idea. You have no idea that you're doing anything useful if you think you're optimizing something without profiling it first. Because it could easily be that 90% of your time is spent in some function that you assume is fast, and the one that you're optimizing is only spending 5% of your time. It's completely useless optimizing a function that's using up 5% of your time. But when you've got low-level access, how do you design libraries that are reusable by people? My example always is parallel sort. You provide a sort algorithm. Well, what if they've got their own data type? They want to write a comparison. How do you provide a library in a form where they can go, yeah, I want this library, but I want it customized to my data type? So I suppose the two approaches that we see as one is the kind of C++ approach, which we like, which is patterns and skeletons. So you have, for example, the C++ parallel STL, which is something that's being developed at the moment, where you have patterns that are actually source code that you can look at and you can modify and you can customize to your own usage. And then the advantage of that is an advanced user can improve the optimization themselves, or compiler transformations like vectorization and scalarization. Only a compiler developer can improve optimization. So that's why people would like to have this. They'd like to have a magic compiler. I should say we had a customer once, and we were delivering their stuff, and all of their presentations started with, this compiler was not magic, right? Compilers are not magic. They can't magically transform it. They follow rules, same as any other software. But if you've got a library, then an advanced user can always modify it themselves. So, I'm coming to the end now, but the tests that I think that you should think about when developing a high-level programming model for people who want to do parallelization and optimization across heterogeneous systems is, does it interoperate with other solutions? Think about, if somebody's already optimized their code with one solution, and they've done a really good job, if you come in with a new parallel programming model that doesn't work with it, you're going to start off day one by slowing down all of their code. So you've got to think about how you interoperate with stuff that people have already used. Can an advanced developer drill down through? Because otherwise, they're going to get to a point where they go, yeah, I need to do this. I need to do it now. I'm not going to wait for you to fix your compiler to make this go faster. Can I do this now? And you should think about that in your design. Can a developer drill down? Can problems like either bugs or performance be followed through a process? So if you say, oh, it's automatic in some vague kind of theoretical way, for an actual engineer doing something, it doesn't always matter if they have to do a certain amount of work. If they know what the work is, it's an awful lot easier than if they don't know what the work is. So think about that. In a real development environment, the closer you can get to saying people, do this, 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 and this, it's actually a lot easier than saying it's automatic. And the last question is it going to continue to work with future processing architectures? Because there's an awful lot of innovation going on in processing models at the moment. And if you're designing something that works with current hardware and not with future hardware, it's the whole classic thing with optimization. You just wait for new hardware to come along and your program goes faster. So my last couple of slides are really, these are the problems that I think that we need to solve. So if you're researchers, these are the things that I think we should focus on. What should a standard toolset for heterogeneous systems look like? Does a normal compiler, linker, executable loader still make sense? One of the problems that we have as a company, and actually all GPU compiler teams have the same problem, is if you hire CPU compiler people, they struggle with GPU compiler development. Because in a CPU compiler, you are dealing with a very clearly defined box. Everyone knows what a CPU compiler looks like. You know what comes in, you know what goes out. An object format goes in, source language goes out. That's it. You only do a compiler. In GPU compilers, it's all joined together. The compiler, the front end, the back end, the linker, the loader, the runtime system, the driver. It's all stuck together in one thing. There is no box. We don't define what that box is. And that's a real problem, actually. We have absolutely no idea how to debug heterogeneous systems. It's a really hard problem. How do you debug completely different processor architectures? It's really hard. What should languages look like? You know, if we've designed all these languages for systems where memory access is virtually free and now it's 1,000 times more expensive, should we make memory access look really expensive in our language? Should we force people to type in an awful lot of stuff in order to access the data and make it very easy to do something like a multiplier, make it look small? And we really haven't got very far with how high-level language features like garbage collection, just-in-time compilation, function pointers are an awful problem. All of these things. So most software is being written in things like JavaScript and Java and C# and all that stuff. And we haven't worked out how to really compile these for these heterogeneous systems. So what do we actually need to build? This is the engineering question. We need really solid tools. They need to be a little bit more reliable than they are at the moment, and they need to work together. We need tools that provide the full development capability, including compiling, linking, profiling, debugging. We need to build debuggers that work for heterogeneous systems. And that does involve some level of working together. And we need libraries that can be user customized and work together with lots of different systems and aren't just specific to specific hardware. And that's it. Thank you for giving me some extra time.
Okay, thanks a lot, Andrew. Questions?
It seems to me that you have as a general assumption C and C++ in your talk. Is that correctly? I mean, is that, you didn't say that explicitly, but that's the feeling I got. But are you also considering, I mean, higher level languages? Or
all of our work as a company so far has generally been on C and C++. But I think that we do need to think about higher level languages.
And are you thinking of high level languages today, or is it just a feeling you have?
I'm thinking about it.
Ah, okay.
We're not building them yet. And that's the real question. And what would it mean to build JavaScript for these things?
What higher level languages would you like? Examples.
I mean, that's a talk in itself, I guess. But I think it's quite clear that C and C++ they are perhaps not on the level of abstraction that we would like them to be suitable for large heterogeneous systems.
I suppose what I'm saying is the ability to do this for higher level languages is kind of there now, but only just now. And it's going to get a lot easier and more possible to be able to do those things. So although we may not have been able to consider compiling Java or Lisp or Haskell to GPU or FPGA, we can now.
Yeah, and perhaps maybe it's not even languages that exists today. Perhaps we need something completely different that we haven't had before.
Well, yes, maybe.
To some extent. I mean, if you're looking at memory accesses, for example, as you pointed out, it's not in any language.
Yep. So building new languages to compile for these systems does seem like a very interesting thing to do. The problem is, how do you get interoperability with stuff that's already running on these systems? That's the question I have. I really have always looked at these systems and went, wow, we could design a language for these things. You kind of end up with Occam, which didn't actually go anywhere. And so rather than theoretically, it introduced lots of theories, but in terms of usage, it's too hard to say to people, rewrite everything. But yeah, if we can come up with that. The one example that I would give is that in our area, in GPUs, shading languages were specifically designed for graphics, and they are phenomenally successful. They're probably the most successful heterogeneous programming language. It's a huge amount of resources in GPUs goes into shading language because they were designed from the start. They pretend that they're C. They look a bit like C. They're not, from a compiler point of view, anything like C. And so the question is, if you design a language specifically for graphics, could you design a language specifically for databases? Say, well, I suppose you have SQL or something, but could you do something like that that could run on a GPU? you know, if you integrate a language with an engine, you know, JavaScript is integrated with the browsers, and there's, you know, Perl and stuff like that integrated with web servers. If you can integrate something with some service that can run on GPUs, yes, I think that could be hugely successful. I don't know what that is, but I think we ought to be able to do that now.
More questions?
Thank you for the talk. I actually am looking at some of these questions with a lot less experience than you. But what my question is that it seems to me that when it comes to performance and optimization, and you're looking at all these different architectures, you might want to follow a process where you're abstracting out some, you know, some things that are common between, you know, different architectures, and then providing some specifics. So something like that you showed with different compilers compiling for different devices. If there is something that is in the upper layer, which is like common to all or most devices that you look for, and then there is something that you know specifically targets a particular device. Maybe that kind of model that we are looking for. What's your comment on that?
Yeah, so the one thing that's common across all devices is the laws of physics are the same for everyone, and so this problem about data movement exists for everyone, but then how people solve that can be dramatically different. So I think if you start to abstract away the cost of data movement, even if it's going to be different on different devices, fundamentally there is going to be different costs for larger amounts of memory than smaller amounts of memory and how you map and move data around. So I think that's generally a common thing. Data parallelism is quite common, but then it's not always appropriate for all algorithms. It's really, I mean, that's why I'm so pleased about we have things like OpenCL SPIR, because then you can hide the instruction set differences underneath. Because the instruction set differences in GPUs are extreme, particularly in our specialist area, which is mobile GPUs. Mobile GPUs do crazy stuff in order to hit performance targets. And so it's good that those things are abstracted away by things like SPIR. It's difficult to make a guess at what those common things are. That's the advantage of the open standards like HSA and SPIR, is that it gives you a layer that you can do those things on.
Okay. A big hand to Andrew Richards.
Thank you.